So Pablo Ramses Alonso Martin, and he has a long title, Statistical Inference for the rough homogenization limit of multiscale fractional Ornstein-Uhlenbeck processes. Thanks.
Yeah, thanks everyone for being here. And yeah, so the title of my talk is a bit long. It's about the statistical inference for the rough homogenization limit of multiscale fractional Ornstein-Uhlenbeck process. And I will spend some time, well, this is joint work with I'm a PhD student at Warwick, and this is joint work with Tessie and Horatio, who are my supervisors. And I will try to first spend some time giving context to the problem and setting up things. And then I will talk about the two main contributions of our work, which, yeah. So first thing is what are the multiscale models we will be looking at, because it's maybe not the exact same thing as the multiscale models that were mentioned before. So what we mean by multiscale models is dynamical system in which some of the components within the model vary at a much faster rate in time than others. And a very illustrative example for this is when you're looking at, for example, atmospheric events, say a storm or a cloud, in which you want to observe, for example, the motion of it to be able to say where is it going to be in the next week or when is it going to come to the UK or things like that. So you want to be looking at the motion of this event in, say, in the scale of hours or days. But then when it comes to this sort of phenomena, there's interaction between particles, for example, that happen at a much faster rate, so say milliseconds or something, and that does have an effect on the motion. So you want to take this into consideration as well. So these sort of things bring a lot of problems. So, for example, in the example I just given, you have to be measuring at the rate of milliseconds for over a week, let's say. So this has a lot of problems when it comes to performing statistical inference in the model. And also it can have all sorts of problems, for example, when you have to handle this much data or how expensive it is to make these measures. So what usually is done in these cases, especially when working with ODEs or SDEs, is find simpler models that usually what they try to do is get rid of the faster varying variables. So for example, I've just written here an example of averaging in SDEs. So what you do in this case, for example, is in this case you have y, the fast variable, and x, the slow one. So what you do is you find an invariant measure for y, and then you integrate in x with respect to that invariant measure. And that way you find an averaged SDE, which now has only one time scale, which is usually the unit of time you're using. And this is, in principle, a much easier model to handle. Because now there's no fine scale appearing there. But the problem is that even though you have a simpler one, it's not very clear how do you fit it. Because so you want to estimate, for example, in this example I'm using here to illustrate, you want to find mu and sigma in this equation to be able to to predict, to be able to perform inference on your model. But the problem is that the nature that you're observing is still a multiscale thing. So you still have, you're not gathering observations from x directly, but from x epsilon, which has the effect of y in it. So the idea is that, sorry, I forgot to mention in the slide before that after so basically the averaged model is a limit when epsilon goes to 0. So when the faster variable varies infinitely fast. So the thing is that, so the idea in this case is that since x is a limit of x epsilon, then they must be close in some sense when epsilon is small enough. So the idea is to hope that the same holds for the parameters when using x epsilon instead of x. So what you usually do is you find the usual estimator you could find for x. So for example here, sigma would represent some quadratic variation. So you find the standard estimator and use the data you observe instead of the original model, and hope that since x epsilon is close to x, then sigma epsilon will be close to sigma. But this is not always the case, and whether or not this is the case, it depends on the scale at which you sample or which you gather observations from your process. So well, I cite here the main references for this is parameter estimation on multiscale models. And for example, in this example that I've used under some general conditions, what you find is that if delta is the rate at which you sample, so the jump between two consecutive observations, then if you attach this to epsilon via some power, then if the power is smaller than 1, then you get the right convergence. But if the power is bigger than 1, then you're not estimating the parameter that you want to estimate. So the meaning of this is that if you sample very, very, very finely at a very fast scale, then you are departing from the parameter you want to estimate, which is a bit counterintuitive because usually when you're performing statistical inference, you want as much observations as possible.
So the limit equation average has additive noise. So sigma squared is not a function but a constant.
Yes. Sorry. Yeah. That's what I'm assuming here. When I said general assumption, maybe it was not that general. Sorry. So what we want to see in our work is what happens here when the multiscale system becomes anomalous in the sense of having what we do is put a fractional Brownian motion in the driving noise instead of a Brownian motion and see how these things behave. So in particular, what we look at is this second order problem, which is this system of SDEs in which basically the fast varying variable is a fractional Ornstein-Uhlenbeck, and then the slow one is just a functional transformation of it, which is scaled so that it has a limit. And then what it's known for this process is that it converges to a scaled fractional Brownian motion in the LP norm, and we take advantage of this to see how to perform inference in this system.
The first equation, right-hand side, doesn't contain differential.
No.
dt or?
Oh, yeah, it should be dt. Sorry. Yeah, sorry. So just quickly some notation. So we will always write little delta to denote the distance between two consecutive observations we make. And capital T will always be a fixed time horizon over which we observe the process. And so basically, the convergence of delta to 0 or n to infinity will be equivalent. So whenever we take a limit, delta going to 0 and there's an n involved, the n is going to infinity at the same time. And then it's very commonly we attach, as in the literature for Brownian motion, we attach epsilon to delta. And the same thing, if we take limit, in this case, when the limit is taken epsilon going to 0, and the other two is the same. And then capital P will be the covariance matrix of the vector of differences of a fractional Brownian motion. So basically, a discretized fractional Gaussian noise. And then, so the setting of the problem is that we have x epsilon converging in the LP norm to sigma times, sigma being a constant, times the fractional Brownian motion. And we want to estimate sigma under the assumption that we only see x epsilon. We also make the assumption that we have access to continuous time samples of the process, in the sense that, of course, you always have to make a discretization to estimate. But what we mean by this is that you can decide the scale at which you sample it from beforehand. And what we want to see is if subsampling is necessary, or at which rate to subsample. And by subsampling, we mean slowing down the rate at which you observe the process. So what we do is, just as in the literature, we derive an MLE for sigma using the limiting distribution, which has this expression. And then what we do is we instead plug our x epsilon there and define our estimator in this way. And then what we want is to find which conditions do we need to impose on delta so that this convergence happens in some appropriate mode. So the thing is that, so to measure the departure between these two, we came across the problem that we need to control the spectral norm of this matrix, which, as I said, is the covariance matrix of discretized fractional Gaussian noise. This is a bit of a parallel problem. Like that doesn't really nothing to do exactly with our problem, but at first we thought that there should be some results for this in the literature, but we didn't find anything, so we had to do it by ourselves. And I thought it was also interesting to comment here as well. So I'm gonna spend some time on this now. So, well, first thing is that now I just add this exponent here, the n, just to make it, to stress that the fact that this quantity will depend on n, on the number of points that the grid has. And we're after some bound of this form. So we want to upper bound the spectral norm of the inverse of this matrix via some sort of thing that will depend on n somehow. And before we so what we want to find is a bound on the asymptotic order, because we already knew from numerical experiments that it blows up with n. So there was no hope to find a bound that vanishes. But we wanted to at least have an idea of what's the order. And even though it may look as a linear algebra problem, because you just have a matrix and you want to find the spectral norm of its inverse, but it turns out that it has a very interesting probabilistic interpretation. And for that, we first use the fact that you can write this spectral norm as obviously is the biggest eigenvalue in the absolute, the biggest eigenvalue because they're positive. So you can also write it as 1 over the smallest one of the original matrix. So that gets, so in that way we get rid of the inverse. And then, so of course, now instead of upper bounding the smallest eigenvalue, we want to lower bound it to be able to put an upper bound here. And lower bounding this eigenvalue is equivalent to lower bounding is a quadratic form on the matrix in this way, because if whatever you put here lower bounds this for any vector u, then it will lower bound all the eigenvalues. And then the icing on the cake for this is to see how a quadratic form on this matrix can be rewritten as the expectation of an integral against the fractional Brownian motion. So if we define calligraphic H to be the space of deterministic integrands for the fractional Brownian motion, and we endow this space with this scalar product, then is when you can rewrite the quadratic form as the H norm of this function f, which is defined here, which is essentially a step function in which each of the values are the vector u you're taking. So now now the problem can be summed up as lower bounding the H norm of a step function, basically. So we split now the case in, because for H bigger than a half and H smaller than a half, the how to find the bound is substantially different. So for H bigger than a half, you can rewrite the scalar product in this way, which is not possible if H is smaller than a half. And then if you define, if these operators are defined generally in L2, this is the fractional integral, and this is one of the possible, but there's many ways to write the fractional derivative. This is just one of them. So if you define these two, you can find they satisfy this relation up to a constant, and then using this relation and also using the adjoint and inverse relation between them, you can lower bound the L2 norm in this way, and then if you rewrite this bound, then this becomes an lower bound on the H norm, taking f and g to be the same. And then working with this bound just explicitly with pen and paper after many pages of calculations, you can find that this ratio is bigger or equal than this quantity here, and that allows to conclude that just putting a square putting a square here using the inequality from before, you can lower bound the h norm of a step function by this quantity, and just by inverting it, you find the upper bound on the quantity that we were looking for. And then for the case capital H is smaller than a half, instead of doing what we did before, we take advantage of the fact that calligraphic H is continuously embedded in L2. To see this, so the H norm of any function f has this expression if H is smaller than a half, and then you can find that for any compactly supported function f, this holds. So then you find that essentially that the LQ norm lower bounds the H norm for any Q in this range, and then up to a constant, and then just by computing the L2 norm of F, you find that in the case H strictly smaller than a half, you have this bound instead. So what we find is that this quantity is bounded up to a constant by n when H is smaller than a half, but n to the power 2h when H is bigger than a half. And although these are just upper bounds, which was enough for our purposes, just by performing some numerical experiments, you can find that here there's for different values of H. So in this side is H bigger than a half, and in this side H is smaller than a half. Computing the ratio in the logarithm scale of the original quantity and the bound we find, you see that it's more or less sharp, at least in terms of the order. There's always a constant. And then once we find this, then the main results of our work are easy to, not too difficult to derive, because we can now measure the departure between our estimator and the original parameter. So the first thing that we find is asymptotic biasness without subsampling. So the first result is that if you don't subsample at all and you just take as much points as you can, so basically if epsilon is fixed and you take delta to be arbitrarily small, then the estimator vanishes almost surely. So you're departing from your original parameter sigma. And if you attach your delta to epsilon, so if you sample at a rate that is related to epsilon from an exponent, then if this exponent is too big, so you're sampling too fast, then it's asymptotically biased. So there's no hope for convergence in any other stronger mode. And then lastly, what we find is that if you instead sample at an appropriate rate, which we find to be in this regime, then you get convergence in L2 at least. So basically what we see is that, as suggested in the literature for standard multiscale systems, in the case of anomalous behavior happening within the dynamics, you observe the same thing. So if you sample too fast, your estimator is going to be biased, whereas if you sample at a rate that is reasonable and is slower than the convergence of the system, then your estimator will be consistent. And then the last thing is some numerical simulations that we perform. This is just the error. So the blue areas is this is the values of alpha. So the values that the exponent you put on epsilon to generate your sampling rate. and this is epsilon going to 0 upwards, and the blue areas is the fastest convergence. So what we see is that the values of alpha don't seem to be dependent on h. Here you have h 0.3, and here is h is exactly equal to a half. And then in the last one, because it didn't fit in the other slide, is h is bigger than a half. And what the most interesting thing we observe from this is that the values of alpha that are valid in some way don't seem to depend on h. And also, there's an optimal value of alpha, which is around 2/3, and is optimal in the sense that the convergence in the estimation happen start happening for the biggest epsilon. So in the sense that when x epsilon is farther from x, if you pick these values of alpha, it seems that your estimator is going to be closer to the true value. But this optimality result, we were only able to prove it for the case h exactly equal to a half, but not for other values of h so far. And this is the same thing for h bigger than a half. And this is all. And we have the paper already on arXiv with the same title as the talk, if anyone is interested. And here are references.